So here is the problem.
Down this name on YouTube.
We have a body, let's call it Earth, drawing a rough circle. And then we have the center of gravity, which we're going to base things off of. Now, the question is, if you're standing on the surface and you suddenly take off to the side at a right angle, how much energy would it take for you to leave the ground and to simply do a spiral off into outer space? And my argument was, well, it would take the same amount of energy that going straight up would do, plus whatever amount of energy it takes to go sideways. So what happens with gravity, start over here and work our way around. Over here, gravity pulls in towards the camera. I'm over here, and I want to take off that way. If I accelerate this way faster than gravity pulls me down towards the earth, I fly. When you have a body and you go around, I'm going to do this as evenly as possible. Here, I'm a terrible drawer. If we're in an orbit around a body, what's happening is, if we're here and we're traveling that direction, as you go forward along this line, what's actually happening is at the same time gravity is pulling you in towards the body. Now, as you go around the orbit, your direction appears to change, and what's really happening is you are falling towards the center of gravity. You're always falling towards that center of gravity. Always. But if you're going forward, you outrun the fall. So by the time you would have fallen to the surface, by the time you would have fallen this distance, you've traveled this distance. You simply outrun the curvature of the planet faster, or at the exact same speed at which you're falling. If you go faster than the speed at which you're falling, faster than the amount of time it takes you to fall, then you leave orbit. You actually travel off into the distance. If you're traveling slower than the time it takes to outrun the balance, outrun the distance to the planet, you travel in towards the planet, and eventually you'll spiral in and crash. Now, earlier today, a friend of mine and I at work, we were taking a break to argue about this question. What would it take to spiral away from Earth if you just suddenly took off running flat and you were able to propel yourself and continue to accelerate even though your feet weren't touching the ground? My argument was it would take escape velocity plus whatever you're adding in to go around. Once you achieve orbit, once you achieve the balance, any additional speed will pull you away from the planet. Any loss of speed will cause you to fall in towards the planet. The reason a lot of satellites seem to want to go back towards the Earth is because once they achieve orbit, they don't really have any more rocket left. So they can't really accelerate, most of them anyway. What happens is there is still some atmosphere, even way out in space around the Earth. It's not a perfect vacuum. So even though they're up there for years, decades, maybe even a century in some cases, we'll still see some of these old satellites floating around up there if we don't do anything about them. They're hitting the atmosphere because even though it's extremely thin, and they call it a vacuum, it's not a perfect vacuum. It's very, very rare. Very rare is a perfect vacuum, even in outer space. That atmosphere is going to slow down the orbiting device just a little bit. That's why they seem like, even though they've been up there for years, they end up falling back towards Earth. The lower they are, the closer they are to Earth, the more atmosphere they're hitting every day. They fall in. Eventually it drags them down. They slow down just that little bit. And what happens when you slow down just a little bit, even just a tiny little bit, you start falling back towards Earth. And if you don't have some way of either boosting yourself or increasing your speed, you're coming back to Earth. this was one of those arguments that we had. I wish I had videoed it because it was when John and I go at it, it's kind of interesting the way we banter back and forth. I really think we were both saying the same thing. He's a mechanical engineer and he knows this stuff backwards and forwards. He was trying to tell me, look, Kelly, I know what I'm talking about. And I'm like, yeah, but it would take the same amount of energy to go up. And I was thinking, he was right, of course. I was thinking that once you achieve orbit, it takes the same amount of energy to go up and increase your spiral as escape velocity. So if you're standing on Earth, you want to escape the gravity well, you've got to push off from Earth hard enough to overcome the gravity so that as you go up, you keep going up. You'll slow down because Earth's gravity is going to drag on you. So as you go up, you're going to slow down and slow down and slow down. And either, like for example, if I jump, you're going to come up to a stop and you're going to come back down. That's what happened when I just jumped. But if you push off hard enough, or if you continue to accelerate hard enough, you're actually going to escape and continue going off out into outer space. That's escape velocity, is when you go off in outer space. It's that perfect balance where you just beat that 0 point. And what I was saying is it would take, let's call that x. So escape velocity is x. It's going to take anything else, no matter what other factors you throw in, it's going to take x plus that other thing. So if I'm taking off sideways, it's still going to take x plus whatever I put into it sideways. And that's kind of what I was trying to say, and I didn't have the words then. And of course, you know, it just does, you never, when you're sitting there, you never have the right way to explain it. So all of this was to say, John, I knew what you were talking about, and it seems like we were both saying the same thing. I was saying it takes escape velocity, and what I meant to say was it takes escape velocity plus anything else you throw into the mix. So it's always going to take at least escape velocity even if you're trying to just do even if you're just trying to make a barely increasing spiral outward, it's going to take escape velocity plus whatever other power you put into it. You're never going to be able to get less than just jumping straight into the air. So it's always going to take that amount of energy plus something else. Now I need John to come back with a video response and say, Kelly, you're full of crap.